Calculus BC, we have graphs of derivatives, part 2. And what we're going to do is, again, take a look at the graph of a derivative. And you can see that we've got f prime given to us. And we know that this derivative, if you just looked at it, would be continuous. That would actually imply that your original function would have to be continuous as well, because that means that you could draw a tangent line anywhere between -3 and 3. But let's do this quickly. We'd like to look at part A and B. We're looking for relative extrema. And, what you want to do, of course, is finding some critical numbers. We'd like to know where f prime equals 0 or where f prime doesn't exist. And very quickly, if y is equal to f prime, I think you can see quickly that there will be 3 x values at -2, 0, and 2, where your f prime value will equal 0. We're going to do a quick number line check and see what's happening. And again, we're right now checking what's happening with f prime. If you look just from -3 to -2, you can see your f prime values, your y values, are above the x-axis. That indicates that f is going to be increasing because f prime is positive. Likewise, if we looked between -2 and 0, you can see our curve is below the x-axis. That's where f prime is negative. That will indicate that f is decreasing. As you go between 0 and 2, again, you can see that your f prime values will be positive. So again, we'll get increase for f. And then from 2 to 3, we don't change sign. We still have a positive derivative. That means f is still increasing. Well, if you were to just connect these arrows, you'd get the top of the mountain, the bottom of the valley right here. Here, as you go up and you go up, you're not going to get an extrema. But, do we have a relative max? Well, yeah, at -2. You can say that there's a relative max at x equals -2. They want us to give a reason how we know that. And that's because f prime changes from positive to negative. You also could say f changes from increasing to decreasing. Well, let's take a look at a relative minimum. Well, we could see that that's at 0. We've got a relative min at x equals 0. We can give a reason. We can say this is going to be because f prime changes from negative to positive. Now, as we look a little further for part C, they just want us to investigate where our graph is concave up. In all truth, though, I think it's way more helpful to investigate the second derivative in general, seeing where your second derivative is going to be 0 or undefined. So let's find where the second derivative equals 0, where the second derivative doesn't exist. And guys, the second derivative is going to be related to tangent line slopes, of course. This is the graph of f prime. F double prime, which is its derivative, is found by the tangent line slopes. So, like if you were to draw a tangent line slope here at like maybe -2.5, you can see that's a negative tangent line slope. Your line is falling. But look what's happening at -1. You would have a horizontal tangent line, wouldn't you? Over here you'd have something positive, but look what's happening at x equals 1. This is also where your tangent line slope would be 0. This last one at 2, oh my goodness, this is the one where kids can forget. If you were to draw a tangent line slope or a tangent line at x equals 2, you'd actually have the x-axis as its tangent line if you think about it. And that would be a slope of 0 also. Then right after that, you can see we'd have positive tangent line slopes. Right before it would have been negative. So I'm going to do a number line. And again, we can only go as far as 3 and negative 3, but I really want to know what's happening at f double prime. The second derivative never was in a situation where it didn't exist. We always have a tangent line slope we can look at. You can see from negative 3 to negative 1, well, we've got negative slopes, negative tangent line slopes. That means f is concave down like a frown. From negative 1 to positive 1, well, you can see we'd have positive tangent line slopes. You can see, just drawing that right there, concave up. How about between 1 and 2? Well, look at that. I'm tracing that over. That's negative. That'd be a negative tangent line slope. You're concave down like a frown. And then between 2 and 3, anywhere on there, you'd have a positive slope. You're concave up. Now, they're asking in part C, the bottom of the screen, for what values is the graph concave up? They're not even asking for where you're concave down or anywhere, but concave up, you can see it's going to be between negative 1 and 1. Notice I'm using open intervals, and 2 and 3. And that's because f double prime is greater than 0 there. Okay? Well, here's the other thing. I know we didn't have to answer this in a particular question, but let's see points of inflection. Do we ever see a change in the sign of the second derivative? We do. Look at x equals negative 1. Your second derivative changes from negative to positive. That is f changes from concave down to concave up. Look at positive 1. Same thing. You get a change from positive to negative for the second derivative. You're changing from concave up to concave down. And finally, at x equals 2, you have that just as well. So we would have 3 inflection points, 3 points of inflection here. Well, they're going to ask for us to make a possible graph. And, I minimized the screen a little bit. Let's do that. I'm going to write this off to the side just so that we might have a little more space. But as we're doing that, we'll say here's 1, 2, 3, here's negative 3, and here's 1, 2, 3 right here. They do want us to have the point negative 3, 0 on f. We want to graph f right here. So we're going to be on the x-axis. There's negative 3, 0. But I guess what I want us to pay attention to, and this is so important for us to be paying attention, we want to be aware as to what's happening. You can see that our curve is going to be going up and then going down, but we're also going to be concave down. So we're going to be going up, and that's going to be moving upwards until we get to negative 2. So here's negative 2, and we're moving upwards, but we're also going to be concave down like a frown. Then what? We're going to be going downward until we get to 0. And as we're going downward towards 0, well, again, the question is how far down should we be going? Well, that's up to you. Rest assured, though, I'm going to be concave down until I get to x equals negative 1. That's concave down like a frown, but then I change to concave up. I'm still going to be going downward, and you can see right here at x equals 0, that's where I'm going to have a min, right? That's going to be a low point. I'm still concave up until I get to x equals 1. And you can see as you look at the derivative, first derivative sign chart, you can see at this point, guys, you're forever going up. You're going to be going upwards forevermore. So that's kind of nice to be aware of. From now on, your curve is just forever rising, but your concavity is going to change. So I'm going to keep going up, but at x equals 1, something changes. I'm going to change from being concave up to concave down. I'm still going up until I get to x equals 2. So I'm concave down like a frown right here. Getting a little sloppy. But at x equals 2, I change now. I'm going to go to concave up like a cup. So that's what these inflection points are really looking like. They're showing where the curvature changes, where you're changing from being concave up to concave down. So hopefully this is making some sense. You can see from this graph there's only a max, a local max over here. There's a local min at x equals 0.